One number, 7 parts in 1,000. Not a probability, not a percentage of anything familiar. It is an exchange rate, the fraction of mass that becomes pure energy when hydrogen fuses into helium inside a star. It is also the reason you have a body. Lower it, 6 parts in 1,000. A proton and a neutron will no longer hold one another. The first rung of the ladder is gone, and nothing climbs. Nothing heavier than hydrogen is ever made. The universe stays as it began. A thin, cooling haze of the lightest gas, drifting outward in the dark. No carbon, no oxygen, no iron, no chemistry anywhere for the rest of time. Now raise it 0.008. Hydrogen ignites too readily. It consumes itself in the first minutes after the Big Bang and leaves nothing for stars to burn. No water is ever made. No world is ever wet. The window is that narrow. The universe landed inside it. And here is where a curiosity becomes a problem. This is not the only number like it. There are 6. They were never found together. They surfaced decades apart in separate fields from people who were not looking for one another's answers. One sets the strength of gravity against the force that binds an atom. One decides how much matter the universe was given. One measures the energy inside empty space, the energy of nothing at all. One fixed the size of the faint ripples left over from the beginning, the seeds of every galaxy you have ever seen. And one settled how many directions you would be free to move in. Only when they were finally laid beside one another did the pattern become impossible to miss. Each one sits in a narrow band. Step outside it, and there is no one here to notice. Physics has known this for 50 years. Physics cannot explain it. What it has produced instead are 3 answers. There have only ever been 3. The first says we were lucky. Lucky past the point where the word still means anything. The second says this universe is one among countless others, nearly all of them barren, and that we could only ever have woken up inside one of the few that works. The third steps outside science altogether. It cannot be tested. It has never gone away. Tonight, we follow all 3. Through a man who described what was inside a carbon atom before anyone had looked, was proved right, and went to his grave without the prize. Through the worst prediction in the history of science, wrong by a factor of 10, followed by 120 zeros. And to a mountain in Arizona, where 5,000 robotic eyes open on the desert sky. Through the night, they swing together, again and again, toward new patches of darkness, gathering light that set out before the Earth existed. What that light carries may end this argument before the decade is out. 6 numbers. Not guessed, measured. And nobody knows why they're right. Start with the sun. Not what it looks like from here, what it is actually doing. At its center, the temperature holds near 15 million degrees, under a pressure beyond anything that has ever existed on Earth. Inside that furnace, hydrogen is being turned into helium at a rate of 600 million tons every second. You would expect that to be violent. It isn't. Take a single cubic meter from the very heart of the sun and measure the heat coming out of it. Around 270 watts, less than your own body produces in the same volume. The reaction is gentle, almost reluctant. The Sun is not a bomb. It is one of the slowest engines in the universe. And that is the reason you are here to look at it. Watch what happens when two pieces of hydrogen actually meet. A hydrogen nucleus is a single proton, nothing else. In the core of a star, protons collide billions of times a second at speeds no laboratory on Earth can reach. Fusion should be effortless there. It is not. Because two protons cannot simply stick together. They both carry positive charge, and like charges push apart. Force them close enough, and the strong nuclear force does take hold, but even then they will not stay. They fly apart almost as fast as they arrive. In our universe, there is no stable particle made of two protons. So for fusion to begin at all, something stranger has to happen first. In the instant those protons are pressed together, one of them has to transform. A proton has to become a neutron, and there is only one force in nature that can do that. In the same moment, it throws off a positron and a near weightless ghost of a particle called a neutrino. That transformation is very nearly impossible. The weak nuclear force earns its name. It reaches no further than a nucleus, and it acts rarely. So a proton sits in the hottest, densest place for light years in every direction, colliding without pause, and waits. On average, it waits about 9 billion years. 9 billion years. One particle, one chance to begin. That is the bottleneck. That is why the Sun glows steadily instead of detonating. Not restraint. Our star has burned for 4.5 billion years because the first step of its own fuel cycle almost never works. After that, everything is quick. The new pairing, one proton bound to one neutron, is deuterium. It captures another proton, and before long, two of those meet and leave behind the finished product. Ordinary helium, where there were once 4 separate nuclei of hydrogen. Now weigh them. 4 hydrogen nuclei in, 1 helium nucleus out. They do not weigh the same. The helium is lighter, not by much, by roughly 7 parts in 1,000. That missing mass did not leak away. It became energy, light and heat, and the outward pressure that holds a star up against its own gravity for billions of years. 7 parts in 1,000. 0.007. We found that number before we had any idea what to do with it. In 1920, a chemist named Francis Aston built an instrument precise enough to weigh atoms against one another, and noticed that helium came in slightly lighter than 4 hydrogens. The shortfall was under 1%. It looked like a curiosity. Arthur Eddington saw what it was. That same year, he proposed that this tiny discrepancy answered a question which had defeated physics for a generation. What keeps the stars burning? Nothing chemical could do it. Nothing gravitational could do it for long enough. But if stars turned hydrogen into helium and pocketed the difference as energy, the arithmetic worked. He had no mechanism. Nobody would work out the reaction chain for another 2 decades. Told the Sun came nowhere near hot enough for anything of the kind, he answered that his critics should go and find a hotter place. Everything since has been detail. Here is what the number means in the star above you. 600 million tons of hydrogen enter every second. Around 596 million tons of helium come out. The 4 million tons unaccounted for become sunlight. And we can prove it is happening tonight. Remember the neutrino thrown off at that first impossible step? Neutrinos ignore matter almost entirely. They leave the core in a straight line and cross to Earth in 8 minutes. Tens of billions are moving through every square centimeter of your body right now. And what little we catch matches the theory almost perfectly. Now change the number. Physicists can ask what a universe would look like if the nuclear binding were slightly stronger or weaker. The results are not subtle. Strengthen it enough to push that fraction to 8 parts in 1,000, and the trouble is not that stars burn hotter. The bottleneck loosens. 2 protons could bind far more easily than they do here without waiting on the weak force at all. Fusion becomes trivially, catastrophically easy. In the first minutes after the Big Bang, when the whole universe was hot enough to fuse, hydrogen would have found itself able to burn without hesitation. It would have, nearly all of it at once, in the opening moments of time. That universe emerges from its own beginning already spent. No reservoir of hydrogen, no slow fuel for stars to work through, and no water anywhere, ever, because the hydrogen that would one day have become water was consumed in the first minutes. Now go the other way. 6 parts in 1,000 instead of 7. Deuterium is the first thing that chain builds, and deuterium is fragile, held by one of the loosest bonds in all of nuclear physics. Weaken the force a little, and that bond does not merely loosen, it fails. A proton and a neutron will no longer stay together at all. And if deuterium cannot exist, the chain has no beginning. Not a slower beginning. None. The reaction that lights every star in the sky has nothing to build from. That universe still forms. It still expands and cools and goes dark. It is simply full of only one kind of matter, hydrogen, and nothing else until the end of time. No heavier elements, no carbon to make a body from, no oxygen to breathe, no iron to carry through your blood. The distance between those 2 universes is 1 part in 1,000. Physicists do argue about how sharp these edges really are. Some have run the models and found the survivable range wider than the standard telling suggests. But notice what nobody claims. No one argues the range is unlimited. The disagreement is over the width of the target, not over whether there is one. Which brings us to the question this film is actually about. In 1999, the British astronomer Martin Rees did something deceptively simple. He took 6 constants that had arrived separately, decades apart, out of fields that barely spoke to one another, and set them down in a single picture. Apart, they were measurements. Nuclear physics had produced one, cosmology another. One had been known since antiquity and never thought of as a number at all. Together, they described something none of them described alone. The conditions required for a universe capable of building complexity. Not a comfortable universe. Not a universe made for anyone. Simply one where atoms could form, stars could burn long enough to forge heavier elements, and matter could gather into things that lasted. The question is not what those numbers are. We know what they are, to more decimal places every year. The question is why they are what they are. And in the middle of the 20th century, one man arrived at that question from the opposite direction. He did not begin with a constant and work out what it permitted. He began with something that already existed, something he was made of, and reasoned backwards to what physics had to be. He was told he was wasting everybody's time. He was right. Look at your hand. About 18% of it is carbon. Not a trace, not an impurity. Carbon is the frame every part of you is built on, the element that makes long molecules possible at all, and there is no other atom in the periodic table that can do its job. It is also the fourth most abundant element in the universe, and, by every reasonable account of nuclear physics, it should not be here. Stars begin by burning hydrogen. When that runs out, the core contracts, the temperature climbs past 100 million degrees, and the star starts working on what is left: helium. The obvious next move is to fuse two helium nuclei together. That does happen. It produces an element called beryllium-8. Beryllium-8 does not survive. It comes apart almost the instant it forms, splitting back into the two pieces it was made from. Its lifetime is so short that the number is difficult to hold in your head. So measure it in distance instead. In the time a beryllium-8 nucleus exists, light travels about 25 nanometers, less than the width of a virus. Then it is gone. So to make carbon, a third helium nucleus has to find that beryllium and strike it within that window. 25 nanometers of light travel, a target that is destroying itself as you aim at it. The universe should have stopped at helium. It did not. And in 1953, a British astronomer sat in an office at Caltech and worked out why. Fred Hoyle was not the sort of man institutions found easy. He had come out of a Yorkshire mill town, largely taught himself as a boy, and arrived in astronomy with a combative streak he never lost. He spent his career attacking the theory that the universe had a beginning, and 4 years earlier, on live radio, had thrown out a dismissive phrase for the idea he was arguing against. He called it the Big Bang. The name stuck. He went to his grave disagreeing with the thing he had named. That was Hoyle, frequently wrong, occasionally spectacularly right, and never quiet about either. He had been working on where the elements come from, and the carbon problem was, to him, not philosophical. It was an accounting failure. The universe was full of carbon. The reaction that ought to make it did not run nearly fast enough to produce that much. Something was missing from the arithmetic. So he proposed a solution nobody had asked for. Atomic nuclei, like everything else in the quantum world, have specific energy levels they can occupy. And if a nucleus happens to have a level sitting at almost exactly the energy that two colliding particles bring to the table, the reaction between them stops being a long shot and becomes overwhelmingly likely. Physicists call it a resonance. It is the nuclear equivalent of pushing a swing at precisely the right moment. Hoyle argued that carbon-12 had to possess an excited state nobody had ever detected, at an energy of roughly 7.7 million electron volts. Not that it might, that it must, because otherwise the carbon in the universe could not be accounted for. He took this to the Kellogg Radiation Laboratory at Caltech and asked them to go and look for it. The reception was not warm. Nuclear physicists did not generally take instructions from astronomers about the interior structure of the nucleus, and the state Hoyle wanted had already gone unnoticed by people whose entire job was finding such things. He was, by several accounts, an irritation. They ran the experiment anyway. It took them a matter of days. The level was there, 7.65 million electron volts, within a fraction of a percent of the value Hoyle had named without ever touching an instrument. And it sits in exactly the place it needs to. The energy that a beryllium-8 nucleus and a helium nucleus bring together is 7.37 million electron volts. The carbon level sits a little above that, close enough to catch the reaction, far enough that the small extra energy available inside a hot stellar core carries it across. The window is narrow. Carbon threads it. But that is only half of what Hoyle found, and the second half is stranger. Once carbon exists, it faces the same danger it just escaped. Another helium nucleus can strike it and turn it into oxygen. If oxygen possessed a conveniently placed resonance of its own, that reaction would run just as efficiently as the one before it, and the carbon a star had painstakingly assembled would be converted almost as fast as it was made. Stars would fill the universe with oxygen and almost no carbon at all. Oxygen does have a level in roughly the right region. It sits at 7.12 million electron volts. The energy needed to reach it is 7.16. It falls just below the line. 40,000 electron volts short, out of 7 million. And because it sits under the threshold rather than above it, the resonance does not fire. So carbon is made by a coincidence, and then survives because of a second coincidence pointing the other way. One level lands just high enough. The next lands just low enough. Move either by a fraction of a percent and you get a universe of helium, or a universe of oxygen. And in neither one is there anybody to notice the difference. Hoyle was an atheist his entire life. Decades later, writing about what he had found, he said that a common-sense reading of the facts suggested a super-intellect had monkeyed with physics. He did not mean it as a conversion. He meant it as an admission that the arrangement disturbed him, and he had no account of it. And here, the story that usually gets told needs taking apart. You will hear this described as the founding miracle of a whole way of thinking. Hoyle reasoned from his own existence, the version goes. He was made of carbon, therefore carbon must be possible. Therefore, physics was obliged to cooperate. Man predicts the structure of the atom from the fact that he is standing there. It is a wonderful story. Historians of science have examined it closely, and it does not hold up. A 2010 study in the Archive for History of Exact Sciences went back to what Hoyle actually wrote in 1953. There is no argument from his own existence anywhere in it. The reasoning is astrophysical throughout, an abundance problem in a paper about abundance, solved with nuclear physics. The dramatic framing appears to have been applied later, over the following decades, partly by others and partly by Hoyle himself in retrospect. That matters, and it is worth being clear about which part is affected. The correction is to the origin story, not to the physics. The carbon level is real, it was measured, and it has been measured many times since. The narrowness is real. The oxygen level sitting just under its threshold is real. What was embellished was the account of how one man came to look. The coincidence survives the correction intact. Only the legend around it does not. What is beyond dispute is what it cost him. In 1983, The Nobel Prize in Physics went to Subrahmanyan Chandrasekhar and to William Fowler, the man whose laboratory had run Hoyle's experiment, for work on how the elements are built inside stars. Hoyle was not included. The decision astonished the field. He had co-authored the foundational paper on stellar nucleosynthesis. He had supplied the prediction that made the carbon pathway work in the first place. It has been suggested that his long public war against the Big Bang did not help him, nor his habit of attacking the Nobel Committee in print when he judged it had passed over somebody else. Hoyle spent the rest of his life outside the establishment he had helped to build, arguing with almost everyone and holding a result he could not explain. He had found a number tuned to within a fraction of a percent, and no reason for it. That was the smallest of the discrepancies waiting in physics. The next one is wrong by a factor of 10, followed by 120 zeros. Take a sealed box and empty it. Pump out the air. Shield it from every field. Remove every particle of matter, every scrap of light, and chill what remains to absolute zero, the coldest temperature that can exist. Now look inside. There is still something there. This is not a philosophical claim. It is the central result of the theory that describes matter at its smallest scale. And that theory is not a fringe idea or a work in progress. It is quantum field theory, and it is the most accurately tested description of nature that human beings have ever produced. One example gives the flavor. The theory predicts a particular magnetic property of the electron, and experiments have measured the same quantity independently. Prediction and measurement agree to around 12 decimal places. That is the equivalent of measuring the distance from New York to Los Angeles and getting it right to within the width of a human hair. Nothing else in science comes close. When this framework speaks, physics listens. And what it says about empty space is this: the vacuum is not a void. It is filled with fields everywhere, and those fields can never be entirely still. Even at their lowest possible energy, they continue to tremble, and that trembling carries energy of its own. We can even feel it. Place two uncharged metal plates extremely close together in a vacuum, and they will be pushed toward one another by nothing at all, by the difference between the fluctuations outside the gap and the fluctuations permitted inside it. The effect was predicted in the 1940s and has since been measured in the laboratory. Empty space pushes on things. So a reasonable question follows. If the vacuum carries energy, how much does it carry? The calculation is not exotic. You add up the contributions of the quantum fields, and you stop counting at the scale where the theory can no longer be trusted. The answer that comes back is enormous. Now go and measure what the universe actually contains. Because vacuum energy does not sit passively, it acts on space itself, pushing outward. Its effect is visible in how the cosmos expands, and that expansion has been mapped with real precision. The two numbers do not match. They do not match by roughly 120 orders of magnitude. Sit with the size of that. In most of science, being wrong by a factor of 1,000 ends an argument. Being wrong by a factor of 1,000,000 ends a career. This is a factor of 10, followed by 120 zeros. Try to find something to compare it against, and the comparisons break. The number of atoms in the entire observable universe, every atom in every star, in every galaxy we can see, is around 10 followed by 80 zeros. So if you had somehow miscounted every atom in existence and got the answer completely wrong, you would still be 40 orders of magnitude closer than this. It is worth being precise about one thing, because it is the first objection a careful viewer will raise. That figure depends on how far down you trust the theory before you stop counting. Choose a more conservative stopping point, and the disagreement shrinks to perhaps 60 orders of magnitude instead of 120. 60, 10, followed by 60 zeros. The most generous possible version of this failure is still, comfortably, the largest gap between prediction and observation in the history of science. There is no second place. And the strangest part is not the size of the error, it is the direction. Because the universe is not showing us an enormous vacuum energy, it is showing us an almost unimaginably small one. Physics predicted a catastrophe, and reality delivered something so close to zero that for most of the 20th century, the sensible conclusion was that the true value simply was zero. That, in a way, would have been the comfortable answer. A zero is something you can explain. Physics is full of quantities that vanish exactly, and behind each one there is usually a reason, a symmetry, a hidden rule, some structural feature that forces the cancellation and leaves nothing behind. If the vacuum energy were precisely zero, then somewhere in the mathematics there would be a principle waiting to be found that made it so. So that is what physicists looked for decades. They never found it. No symmetry has ever been discovered that forces the vacuum energy to cancel. And every attempt to construct one has failed, usually by breaking something else that we know to be true. Which leaves the question that makes this the deepest problem in physics, rather than merely the largest. Not, why is it zero? But, why is it this? Because the value we observe is not zero. It is a small, specific, stubbornly non-vanishing quantity. The survivor of a cancellation that had to run to more than 100 decimal places and then stop, leaving a whisper behind. Nothing in any known theory explains why a cancellation would be that precise and yet incomplete. And here the story stops being an accounting puzzle and starts being about you. Vacuum energy behaves unlike anything else in the cosmos. Ordinary matter thins out as space grows. Spread the same material through a larger volume and its density falls. The energy of empty space does not do that. It is a property of the space itself. So the more space there is, the more of it there is. It does not weaken as the universe expands. It compounds. Which means it competes directly with gravity, and the competition decides whether anything is ever built. In the early universe, matter is spread almost perfectly evenly, with only the faintest variations in density. Gravity works patiently on those variations for hundreds of millions of years, pulling the slightly denser regions together until they collapse into the first structures. Every galaxy that exists is the end product of that slow accumulation. Raise the vacuum energy, and you give the outward push a head start. Space begins expanding faster than gravity can gather anything. The faint overdensities are pulled apart before they can deepen. Nothing collapses, nothing accumulates, and the result is not a difficult universe. It is not a universe where life struggles but persists somewhere. It is a universe with no galaxies at all, no stars, because there are no collapsing clouds to form them. Matter thinning out forever into cold, featureless, uninterrupted dark. Push the value the other way and make it sufficiently negative, and the failure is the mirror image. Space stops expanding and falls back inward, collapsing on itself long before anything interesting has time to happen. So there is a range. Outside it, in either direction, the universe builds nothing. We are inside it. And the theory that describes the vacuum better than any theory has ever described anything overshoots the answer by more zeros than there are atoms in the sky. For most of the 20th century, that was where the matter rested, an embarrassment too large to solve and too fundamental to ignore. Physicists worked around it, waited for a symmetry that never arrived, and largely agreed on one thing. Whatever the eventual explanation turned out to be, it would be a real mechanism. Something in the equations. A reason. Then, in 1987, one man stopped waiting. He was among the most accomplished theorists alive, and one of the most forceful atheists in 20th century science. The argument he was about to reach for was one he had spent his career regarding as a retreat from proper physics, the kind of reasoning serious people used when they had run out of ideas. He used it anyway. And it produced the only successful prediction anyone has ever made about this number. Steven Weinberg was not a man who reached for comfortable answers. In 1979, he shared the Nobel Prize for showing that two of the four forces of nature, electromagnetism and the weak interaction that governs radioactive decay, are not two forces at all. At high enough energies, they are a single thing wearing two masks. It is one of the genuine unifications in the history of physics, and it came from exactly the kind of work Weinberg believed in: hard mathematics, producing a mechanism, producing a testable consequence. 2 years earlier, he had written a book about the first moments of the universe and closed it with a line that people are still arguing about. "The more the universe seems comprehensible," he wrote, "the more it also seems pointless." He was an atheist, publicly and without much diplomacy about it. He thought the cosmos owed us nothing and had been built with nobody in mind. And he had spent his career regarding a particular style of argument as barely physics at all. That argument is worth understanding before we watch him use it. Suppose you want to know how deep a river runs. So you wade across at a dozen different points, and at every one of them, the water comes up to your waist. You conclude the river is shallow. You are wrong, and the mistake is not in your measurements. It is in the fact that you could only take measurements where you were able to stand. The deep sections are still there. Your method simply could not sample them and return. That is a selection effect. Your observations have been filtered, not by nature, but by the requirements of the observer doing the observing. Applied to the universe, the reasoning goes like this. Any measurement of the constants of physics is being taken by something that exists. And things like us can only exist in a universe where the constants permit things like us. So we should not be surprised to find the numbers hospitable. Any value that wasn't would have no one available to write it down. As logic, this is unobjectionable. As an explanation, most physicists found it close to worthless. Because look at what it does not do. It identifies no mechanism. It names no force, no symmetry, no equation. It tells you nothing you could have used in advance. And it has an unpleasant habit of arriving at exactly the moment when someone has run out of ideas. A way of declaring a problem solved by pointing out that we are here to have it. Weinberg shared that distaste completely, and in 1987 he published a paper that used the argument anyway. His reasoning was disciplined, and it went in a direction nobody had taken seriously. He did not ask what the vacuum energy is. He asked a narrower question. What values would be consistent with the existence of anyone able to ask? We already know what happens if that number is too large. The outward push overwhelms gravity before matter can gather, and nothing is ever assembled. No structures, no stars, no chemistry, and nobody. So there is a ceiling. Above a certain value, the universe is permanently empty of observers. Weinberg worked out where the ceiling sat, and when he had it, something about the answer was strange. The ceiling was not remote. Physicists at the time overwhelmingly expected the true value to be exactly 0, cancelled to nothing by some principle still waiting to be discovered. But the maximum value compatible with galaxies was not enormously far above the tightest observational limits of the day. It was close. A couple of orders of magnitude, in a problem where the numbers in play ran to 120. Weinberg saw what that proximity implied. If some deep symmetry forces a quantity to 0, that quantity has no reason to land anywhere near a boundary defined by the existence of galaxies. Those two things have nothing to do with one another. A number driven to 0 by mathematics does not care what conditions astronomers require. Finding it just beneath that ceiling would be a coincidence with no explanation behind it. But if the value were not fixed by any principle, if it were, in effect, arbitrary, and the only filter on it were that observers had to be possible, then the situation reverses. Most arbitrary values are too large and produce empty universes. The ones that survive the filter cluster below the ceiling, and there is no particular reason for them to sit far below it. So Weinberg made a prediction, and it contradicted the consensus. The vacuum energy is probably not 0. It is probably small and non-vanishing, and not very far under the maximum that permits a universe with galaxies in it. Then he waited 11 years. In 1998, 2 teams of astronomers went looking for something else entirely. Both were using exploding stars of a particular type, objects that detonate with almost identical brightness, so that how dim they appear tells you how far away they are. Collect enough of them at enough distances, and you can reconstruct the history of the expansion. They expected to measure how much the expansion had been slowing down. Gravity pulls. The universe has a great deal of matter in it. The only real question was the rate of the deceleration. The distant supernovae came back too faint. Not by much, but consistently and in the wrong direction. The universe had not been slowing. Somewhere around 5 billion years ago, it had begun to speed up, and it had been accelerating ever since. The first reaction in both groups was that something had gone wrong with the analysis. They looked for the error for months. There wasn't one. The 2 teams had worked independently, with different methods and different data, and they had arrived at the same answer. Empty space carries energy. The number is not 0. It is tiny and it is real, and it sits in the region Weinberg's reasoning had marked out over a decade earlier. it remains the most successful prediction anyone has made about this quantity. And Weinberg never treated it as a triumph. He wrote, plainly, that essentially every working physicist would prefer a non-anthropic explanation, and left no doubt that he counted himself among them. He had not converted. He had done a calculation, followed it where it went, and published a result he found unsatisfying. Because the alternative was to keep waiting for a mechanism that 50 years of searching had failed to produce. He spent the rest of his life open to a better answer arriving. It never did. That is the uncomfortable shape of this chapter. The one prediction that worked came from the one argument nobody wanted. But there is a problem inside it, and Weinberg understood the problem perfectly well. Go back to the river. The reason that story works is that the river has deep parts and shallow parts, and you sampled the shallow ones. No variety, no selection. If the river ran uniformly waist-deep everywhere, then wading across and finding waist-deep water would tell you nothing about your method. It would only tell you about the river. So when we say the constants had to permit observers, we are quietly assuming they could have been otherwise. That somewhere the other values must also exist. If this universe is all there is, and its numbers were never able to be anything else, then the anthropic argument explains nothing whatsoever. It becomes a sentence that is true and useless. Of course the conditions permit us. We are here. Which means the prediction that worked comes with a debt attached. To make it more than a tautology, you need the other values to be real somewhere. You need more universes. Otherwise, there is nothing for the selection effect to select from. A great many more, perhaps infinitely many. That is an enormous thing to ask for. Other universes. Not other planets, not other galaxies, entire separate regions of reality with their own physics, permanently beyond anything we could observe. Asked for, apparently, because we have a problem here that we cannot otherwise solve. Any theory in trouble can be rescued that way. Invent something unobservable, place it beyond reach, and declare the difficulty handled. It is one of the oldest bad moves in science, and if that were what happened here, this chapter would be very short. So the honest test is this. Did anyone have a reason to believe in other universes that had nothing whatsoever to do with the numbers we have been discussing? They did. 2 reasons from 2 directions, neither of them looking for this. Start with the first one, and with a problem that has nothing to do with fine-tuning at all. Look at the oldest light in the sky, the faint glow left over from when the universe first became transparent. It arrives from every direction, and its temperature is almost exactly the same everywhere. Point a telescope one way, then point it the opposite way, and the 2 patches of sky agree to within 100,000th of a degree. They have no business agreeing. Those 2 regions have been separated since the beginning. In the standard picture, light has never had time to travel from one to the other. Nothing has ever passed between them. They could not have exchanged heat, or settled into equilibrium, or communicated in any way. And yet they are at the same temperature to 5 decimal places. There was a second puzzle alongside it. The geometry of space appears to be almost perfectly flat when the equations allow it to curve, and any tiny deviation early on should have been amplified enormously over billions of years. To be this flat now, it had to have been unimaginably flat then. In 1979, a young American physicist named Alan Guth was not working on either of these questions. He was working on something else entirely, an embarrassing prediction in the leading theories of the day that the universe should be littered with a certain kind of exotic heavy particle nobody had ever seen. While chasing that, he noticed that the early universe could have gone through a brief episode of runaway expansion. Not the steady growth we see now, something violent and brief, a fraction of a second in which space doubled and doubled and doubled again, dozens of times over. And that one idea cleaned up everything at once. If a tiny patch, small enough to have been in contact with itself, was suddenly stretched to enormous size, then the whole observable universe would be the expanded image of a region that had once been in equilibrium. Of course, the sky is the same temperature everywhere. It was all one place before it was blown apart, and stretching any curved surface far enough makes it look flat. The flatness stopped being a coincidence and became a consequence. The idea is called inflation, and this is the crucial part. It was not proposed to explain the constants. It was proposed for other reasons. It solved problems it had not been aimed at, and then it did the thing that separates physics from storytelling. It made a prediction. Inflation says the microscopic quantum fluctuations present during that expansion would have been stretched along with everything else, seeding faint variations in density across the sky, with a particular statistical signature. Decades later, satellites mapped that ancient light in fine detail and measured the pattern. It matched. So inflation earned its place. And then, once physicists began working through its consequences, it produced something nobody had asked for. In most versions of the theory, inflation does not stop cleanly. It ends in patches. In some regions, the field driving the expansion decays. Inflation switches off, and that region settles down into an ordinary universe, evolving at an ordinary rate. But the space between those regions is still inflating, and it is inflating faster than the calm patches can spread into it. Which means inflation never ends globally. It ends locally, over and over, forever. Each time it does, a new region is opened up, expanding into a history of its own. And the inflating background continues between them, producing more, without limit. Nobody designed this. It fell out of the equations of a theory built to explain the temperature of the sky, and most of the physicists who found it were not pleased to have it. That is the mechanism. Now, the second thread, from a completely different part of physics. For half a century, the deepest unsolved problem in theory has been that our two great descriptions of nature do not fit together. The theory of gravity and the theory of the very small work beautifully apart and contradict each other where they meet. String theory is the longest-running attempt to reconcile them, and it comes with a requirement that has always been hard to swallow. It needs more dimensions of space than the three we move through. The extras have to be curled up small enough that we never notice them. And here is what matters. The way those extra dimensions are folded is not incidental decoration. It determines the physics that plays out in the dimensions we can see. Which particles exist, how strongly they interact, what the constants come out to be. Physicists went looking for the folding that produces our universe. They found that there is no single answer. There are a staggering number of stable ways to fold those dimensions, each one yielding a different set of physical laws. The figure most often quoted is 10 to the 500th power, and that number is a rough estimate rather than a measurement, but the scale of it is the point. String theory does not predict one universe. It permits an immense catalogue of them, each with its own values for the quantities we have spent this film worrying about. This was not a triumph. It was received by many of the people who found it as a disaster. A theory meant to explain why physics is the way it is, revealing instead that it could have been almost anything. Now put the two threads together. Eternal inflation supplies the machinery to make regions endlessly. The landscape of folded dimensions supplies the variety, so that different regions can settle into different laws. Between them, they deliver precisely the structure that was demanded at the end of the last chapter. A population. And variation across it. And with that in place, the problem changes shape entirely. Because the question is no longer why our constants have the values they do. In an ensemble that vast, every permitted combination occurs somewhere. Most of those regions are sterile, expanding into cold nothing, or collapsing before anything forms, or filled with matter that can never build a molecule. They are not rare. They are the overwhelming majority. Nobody is standing in any of them. The regions where anyone exists to take a measurement are, necessarily, the ones where the numbers permit existence. Not because anything arranged them that way, because the others produce no one to ask. So the tuning is not a target that was somehow struck. It is the only address at which the question could ever be raised. Nothing needs to have been deliberately set. No external choice is required. The numbers themselves are no less extraordinary. What changes is that finding them is no longer surprising, because finding requires a finder. That is why a great many working cosmologists regard this as the answer. And it is not laziness on their part. It requires no new mystery. It follows from two frameworks that were built for other purposes and confirmed on other grounds. And it dissolves a problem that 50 years of searching for a mechanism had failed to solve. It is also, obviously, difficult to test, though not quite as untestable as its critics sometimes suggest. If our bubble ever collided with a neighboring one, the impact could have left a faint circular bruise in that ancient light. People have searched the sky for it. Nothing conclusive has turned up, but the search is real, and it could, in principle, succeed. So the case is strong. It is coherent, it is economical, and it is held by serious people for serious reasons. There is only one difficulty. To claim we should expect to find ourselves in a region like this one, you have to be able to say what is typical across the ensemble. You have to be able to count. And when physicists tried to count, something broke. Not an objection raised by critics from outside, a failure discovered inside the mathematics by the people building the theory. More than 2 decades later, nobody knows how to fix it. The whole argument rests on a word that sounds harmless. Typical. We are typical observers. Our region is a typical region among those that contain anyone. That is what licenses the conclusion, not that our universe is special, but that it is ordinary among the ones where the question can be asked. To say that, you have to compare. And to compare, you have to count. Try counting the whole numbers. Now count how many of them are even. Half, obviously, 1 in every 2. But nothing forces you to count them in that order. Take them in a different sequence. 1, 2, 4, 3, 6, 8, 5, and run the same tally, and the fraction that come up even is different. Change the order again, and it changes again. Both orderings contain every number. Neither leaves anything out. They simply disagree about what proportion of an infinite collection has a given property. That is not a trick. It is what infinity does. Ask what fraction of an endless set is anything at all, and the answer depends entirely on the order you chose to count in. Eternal inflation produces an endless set of regions. So to say that observers like us are typical, you must first choose how to count them, which regions to tally first, where to draw the boundary, how to compare one infinite population against another. Physicists call that choice a measure, and there is no agreed one. Several reasonable candidates exist. They are all defensible. They are built on different, sensible principles, and they contradict each other. One measure says observers like us are common. Another says we are freakishly rare. Another predicts we should almost certainly find ourselves much earlier in cosmic history than we do. Nothing in the physics selects between them, which leaves the theory in a strange condition. Without a measure, the multiverse makes no prediction whatsoever. It says every permitted arrangement occurs somewhere, which is compatible with any observation you could ever make. A framework that permits everything forbids nothing, and a theory that forbids nothing has told you nothing. That alone would be serious. What comes next is worse. Take any measure that weights regions by how long they last and follow it far enough forward. Our universe is expanding, cooling, running down. Given enough time, vastly more than has passed, matter disperses, stars burn out, and what remains drifts toward a thin, uniform warmth with almost nothing happening in it. But not quite nothing. Random fluctuations continue forever. And given unlimited time, a fluctuation of any size will eventually occur, including one that assembles a functioning brain. Not a planet, not a civilization, just an observer, briefly coherent, holding a complete set of memories of a life that was never lived and a universe that was never there, before dissolving back into the warmth. Such a thing is fantastically improbable. But it is far less improbable than the alternative, a fluctuation that produces an entire structured cosmos, with galaxies and stars and a history behind it, is more improbable still, by an unimaginable margin. And over infinite time, the merely astronomical outnumbers the truly absurd without limit. So under many of the measures on offer, isolated fluctuation observers outnumber ordinary ones. Not slightly, overwhelmingly, which means the theory makes a prediction about you. It says you are almost certainly one of them, that the room around you is not there, that your memory of the beginning of this documentary was assembled a moment ago, complete, and is about to end. And here is why physicists treat that as fatal rather than merely unsettling. If it were true, every piece of evidence you have would be fabricated, including the observations of the sky that led to inflation and the measurements that supported it, and the reasoning that produced the multiverse in the first place. The prediction destroys its own foundation. A theory that concludes your data is invented has removed the grounds on which anyone believed it. So the result is used as a filter. When a model predicts that fluctuation observers dominate, that model is generally taken to have failed. Not because anyone dislikes the conclusion, but because the conclusion is self-defeating. Several natural formulations of eternal inflation fail exactly that test, which is where the mainstream answer stands. Choose no measure, and the multiverse predicts nothing at all. Choose one of the obvious measures, and it predicts something that cannot be believed without abandoning the evidence for it. The task of the last 20 years has been to find a measure that avoids both. And there are candidates, and they are ingenious, and none of them has won agreement. None of this proves the multiverse wrong. It may be entirely correct. What it means is that the escape hatch has not yet been shown to lead anywhere. That the most popular explanation for the 6 numbers cannot currently be made to say anything definite about them. So we are left where we started, with better company. 3 answers: luck past the point where the word means anything, an ensemble whose mathematics does not yet work, and something outside science that will not go away. For 50 years, that was the whole of it. A question you could take a position on, argue about at conferences, and go home from unchanged. No experiment touched it, no measurement moved it. That is no longer true. Something has begun to shift in the data, and one of the 6 numbers may not be a constant at all. There is a mountain in the Arizona desert with a telescope on it that has been staring at this problem every clear night for years. At the top of the instrument sits a plate holding 5,000 optical fibers, each one mounted on its own small robot. Before every exposure, all 5,000 swing at once, a few seconds of coordinated motion, and each fiber settles onto the position of a single distant galaxy. The shutter opens. The light of 5,000 galaxies runs down 5,000 threads of glass. Then the robots move again, and again, all night, every night. It is building a 3-dimensional map of tens of millions of galaxies, stretching back billions of years. And it is doing that for one reason. Buried in the early universe is a fixed length, a scale imprinted on matter when the cosmos was very young and frozen there ever since. It works as a ruler. Find that same length at different distances and therefore at different moments in the past, and you can read off how quickly space was stretching at each of them. Measure that history precisely enough, and you can answer a question nobody could touch before. Has the energy of empty space always been the same? For 25 years, the answer was assumed to be yes. That is what makes it a constant. It has one value. It has always had that value, and it will hold that value forever. The map is beginning to suggest otherwise. Combined with supernova surveys and the oldest light in the sky, the data now hint that this quantity may have been slightly stronger in the past and may be weakening as time goes on. Depending on which datasets are combined, the statistical significance runs from about 2.8 up to 4.2. That is genuinely interesting, and it is not yet a discovery. Physics has watched results at this level dissolve before, promising signals that grew clearer for a while and then vanished when better data arrived. Anyone telling you this is settled is ahead of the evidence. But it will not stay unsettled. A new survey telescope in Chile has begun imaging the entire southern sky repeatedly for a decade. A European spacecraft is mapping the shapes of billions of galaxies from orbit. Another observatory is being prepared to join them. Together with the machine in Arizona, they are expected to pin this quantity down to better than 1% within about 5 years. That is the difference between this chapter and every chapter before it. Everything else in this film has been argued, reasoned about, defended, attacked, and left standing. This is going to be measured. And the two outcomes lead somewhere entirely different. Suppose the value holds steady, then nothing here has changed. The vacuum energy is a true constant, sitting at a number that no theory predicts and no symmetry explains, inside the narrow band that permits a universe with anything in it. The three answers remain exactly as they are: extraordinary luck, an ensemble whose mathematics has not yet been made to work, or something outside the reach of any equation. Choose according to temperament, because the evidence will not choose for you. But suppose it is changing. Then it was never a constant at all. It is a process, something unfolding, with a past and a future and a rate. And that changes the kind of question it is. A dial that was set demands to know who set it. A process demands to know how it works. Physics has spent 50 years hunting for a mechanism behind this number and finding nothing, in part because there seemed to be nothing to explain beyond a single fixed value. A quantity that evolves has behavior. Behavior has causes. It becomes the sort of thing the ordinary methods of physics are actually built to attack. And for the first time, one of the 6 might be dislodged from the list of things that simply are and moved on to the list of things that happen. It would be the first crack in the problem in half a century. It would also, and this matters, only be one of them. 5 numbers would still be sitting there, unexplained in their narrow bands. Nobody is about to hand you an answer to all of it. Still, consider where this has arrived. For 3,000 years, the question of why anything exists in a form capable of holding us was a matter for philosophy. It was asked in temples and lecture halls and answered by argument, and no argument ever closed it. For the last 50, it belonged to physicists who could calculate the constants precisely and explain none of them, and who argued about it at conferences and then went home unchanged. It has never once been decided by an instrument. Tonight, on a mountain in Arizona, 5,000 small machines are turning together in the dark, gathering light that left its galaxies before the Earth existed. In Chile, a shutter is opening on the southern sky. Above both of them, a spacecraft is measuring the shapes of galaxies too faint to see from the ground. None of them care what anyone believes. They are simply collecting the light, night after night, and the number is going to come out. Somewhere in this decade, an argument that has run for 3 millennia is going to receive its first piece of hard evidence. 6 numbers. One of them is about to start talking.